Hello, this is Part B of the Chapter 9 lesson. In Part B, we're going to introduce an idea called linear regression. And the calculations here can get somewhat complicated, and like always, we're not going to focus on doing those calculations by hand. We're going to focus on understanding what it is we're doing and what it all means, and we're going to let the Excel do the number crunching for us. And so in regression, there's two basic goals. Number one, we're going to look for relationships between variables. This is a similar goal to what we had in Part A of this lesson. And then the second goal is to make predictions. And a very important point to remember about regression is that when doing regression, we're looking for relationships between variables. We're not looking for cause and effects. Cause and effect is a whole other issue outside of the realm of statistics. We are looking for statistically significant relationships. Just because there's a relationship between two variables does not mean that one causes the other. Always keep that in mind when doing statistics. Okay. So the first example we're going to look at is example 9.1 from the Excel guide. And the question that we want to try to answer is there a relationship between a person's age and systolic blood pressure? And so in this example, we have two types of variables, or any type of regression problem, we have two types of variables. We have the first one that we call the response, or the dependent variable, and the second type is called the predictor, or the independent variable. So in this case, our response variable is systolic blood pressure, and we're going to denote that with the variable y. And the predictor variable is age, which we're going to denote with the variable x, or with the letter x. So response, we can think of systolic blood pressure as a response to age. We could also think of age as something that we're going to use to predict systolic blood pressure, hence the names. A dependent we can think of as meaning that systolic blood pressure depends on age. Age we can think of as independent because we're assuming right now that nothing else is affecting age, and so that is not affected by systolic blood pressure. So the Excel guide contains a bunch of data which I've already entered for you in the workbook Chapter 9 in the worksheet regression. We have here is information from I think 40 different people. For each person we have their age in years, their sex, 1 meaning male, 0 female, and then a lot of other information. BMI, body mass index, systolic blood pressure, diastolic blood pressure, total cholesterol, HDL cholesterol, diabetes, where 1 means that the person has diabetes, 0 does not. Smokes, 1 means that the person does smoke, 0 means that the person does smoke. And so we'll be using several columns of data here in this lesson and the next part. Okay. So the first thing to look for a relationship between age and systolic blood pressure is to form a scatter plot. And we talked about how to do this back in earlier in the semester. And so we're going to put age on the horizontal axis. Age is our independent variable. And remember back to high school algebra, we always put the x variable on the horizontal axis. So our independent goes on the horizontal, the dependent goes on the vertical. And so we form a graph of this. And some observation that we want to make here is that as we move from left to right, age increases. We'll look at what happens to those dots. Kind of in general, they typically go up. And so as they go up, that means systolic blood pressure increases. And so as age increases, systolic blood pressure tends to increase. And also note that we could kind of draw a straight line through those dots that captures the general trend of those straight dots. And so we're going to have to use our imagination a little bit to see that straight line, but we can draw a straight line that captures the general trend of that data. And so because of that, we say that there is a positive linear correlation between age and systolic blood pressure. Correlation is just a fancy name for relationship. Linear means that a relationship can be described by a straight line. positive means that that line slopes up from left to right. Remember back to high school algebra, if we had a positive slope to a line, that means it goes up from left to right. So positive linear correlation between these two variables. Now, the next thing that we want to do is measure the strength of that relationship. We're going to measure this with a quantity that will denote R, which is also called the linear correlation coefficient, or called the Pearson correlation coefficient. Pearson was a famous statistician who did some pioneering work in the early 1900s. R measures the strength of a linear relationship, and it takes values between a -1 and a +1. If we have a value close to -1, that means we have a strong negative correlation. If the value is close to +1, that means we have a strong positive correlation. If it's close to 0, then that means there's not a relationship at all between the two variables. So here's a formula that we can use to calculate R. Don't let it scare you because we're not going to use it. We're going to let Excel do the work. But what the point of this formula is that we can just simply use the X and Y values from our data. N is the number of data points, and we crunch all those numbers, and that's how we get R. So let's look at some examples of some graphs and the corresponding values of R. So in each one of these graphs, we have graphed a dependent variable versus an independent variable, and we see that these different types of graphs form different types of relationships. So here we notice that these dots form dots that lie very close to a straight line that slopes down from left to right. And so we say that the variables in this graph have a perfect negative correlation, and the R value would be -1. Here, notice that the dots form not quite as perfect a straight line as over here. So we say that those two variables have a strong negative correlation, and so we'd have an R value very close to -1. Over here, the dots form kind of a straight line that slopes down from left to right, but not near as perfect as these over here, or as strong as this one here. So we'd say it has a weak negative correlation. So we'd have a negative value of R, like maybe -0.7. Then here are some examples of positive correlations. If we look here at this graph, notice that they form a very strong or almost perfect straight line that slopes up from left to right. So we say that those two variables have a perfect positive correlation. Here we have a strong positive correlation, so an R value very close to +1. Here they have a weaker positive correlation, so we'd say these have a weak positive correlation with an R value not as close to 1 as these other examples. Here's an example where there just isn't any sort of pattern at all to those dots. So in this case, we'd say that there's no linear correlation, and we'd have an R value very close to 0. Over here, these dots do form a pattern, but it's not a straight line pattern. It's just these variables would have what we call a nonlinear relationship, and they'd have an R value very close to 0. So that gives you an indication as to what the R value means graphically. Now let's look at how we can actually calculate it. Formulas for calculating the value of R and all the other formulas in this section, in this lesson, are built in. So if we go to the worksheet regression, and then go to your data tab and data analysis, and we see kind of in the middle we have this option for regression. If you highlight that, press OK, you're going to get a window that looks like this. Here, the input Y range, you're going to enter your values of Y, which in this case is in column D. And then the input X range, these are your independent variables. In this case, the X values are the age, the Y values are the systolic blood pressure. Check the box next to labels, because our first row of the data contains labels. And then next to output range, select a blank cell. I've selected K1, but there's nothing special about that. A lot of other options that we can check here, but we don't need any of those, so then we press OK. And we get a whole bunch of different outputs We're going to look at all of them eventually, but let's look at just the first set of outputs here. The first set is titled Summary Outputs, and here in the first line is called multiple R. That is our value of R. Excel calls it the multiple R value, and it uses capital R instead of lowercase r, but it doesn't really matter what you call it, it's the same thing. So that's our value of R, 0.4 roughly. R squared, that's just the square of that R value. Then there's adjusted R squared value, which is similar but calculated using a little different formula. Standard error, we'll talk a little bit about what that means here in a bit. Observations 40, that means we simply have 40 data points. And so R is 0.4, which is positive, but it's not a very large positive number. And so our conclusion is that there appears to be a weak positive correlation between age and systolic blood pressure. So that's kind of the answer to our first question for regression. Is there a relationship between these two variables? Based off of our observations and our calculations, it appears that there is. So now the next question is, can we predict a person's systolic blood pressure if we know the person's age? And so what we're going to do here is assume that in the population of all people, age and systolic blood pressure are related according to a formula that looks like this. Systolic blood pressure is some constant that we'll call beta naught plus another constant called beta 1 times the age. Or if we use the variable y to denote systolic blood pressure and x to denote age, the formula looks like this. Beta naught is called the intercept and beta 1 is called the slope. Remember back to high school algebra, we had something we called the point slope formula, or the slope-intercept formula of a straight line, which is y equal mx plus b. This is kind of the same thing. This is y equals mx plus b. Here we're using beta 1 for m and b naught, or beta naught for b, but same basic idea. Slope and intercept. So now we want to estimate the values of beta 1 and beta naught using our data. We don't have information from our entire population of people, so we're not going to be able to know the exact values of beta naught and beta 1. So we're going to use our sample data to try to estimate them. And here's some formulas that we can use to estimate them. Again, don't let these formulas scare you because these formulas are built into Excel. Beta naught we're going to estimate with the number that we call B naught, which is given by this formula. Beta 1 we're going to estimate by a number we call B1, which is calculated using this formula. And then when we calculate B naught and B1, we're going to put those into an equation like this that we call the regression equation. And so the regression equation has this general form: y hat equals B naught plus B1 times x. We'll talk about the significance of the hat here in a minute. But so we'll go back to the worksheet regression. Now we don't have to do any more work to calculate this regression equation. Excel has already done it. If we look further down into our results, we'll see cells that look like this. That are titled coefficients. Coefficients are generic names for these constants B naught and B1. And so here's the intercept. That right there is our value of B naught. And then the coefficient of age. That's another name for the slope, or the value of B1, so 0.56 roughly. And so there's our regression equation. Y hat equals 89.4 plus 0.56x.